we have been fed a lie about the void. For decades, we pictured deep space as the ultimate freezer, a domain of absolute biting stillness where temperature drops to the physical limit of zero. We imagined that if you stepped out of a spaceship between galaxies, you would instantly freeze to the absolute bottom of the thermodynamic scale. But this is wrong. The universe is not frozen. It is actually simmering. The vacuum of space is alive with the leftover heat of creation, a bath of ancient radiation that prevents the cosmos from ever truly reaching zero. But here is the revelation that defies logic. Deep in the constellation of Centaurus, there is an object that has broken this rule, a massive, ghostly cloud of gas that has somehow managed to become colder than the empty space surrounding it. It is the only natural place in the cosmos colder than the afterglow of the Big Bang itself. If you want to understand how a dying star can break the laws of physics to create a pocket of impossible ice in a universe of fire, hit that like button and subscribe. We are about to dismantle everything you thought you knew about cold. Prepare yourselves. Let's begin. To understand why this anomaly is so shocking, we must first establish the thermal flaw of our reality. When we look at the dark gaps between stars, our eyes tell us there is nothing there. But if we could see in the microwave spectrum, the sky would not be dark, it would be glowing. This glow is the cosmic microwave background, or CMB. It is the fossilized light from the infant universe, released 380,000 years after the Big Bang, when the cosmos finally cooled enough for light to travel freely. Over 13.8 billion years, the expansion of space has stretched this light, cooling it down from a blinding primordial flash to a faint microwave hum. This hum sets the temperature of empty space at exactly 2.7 Kelvin. That is minus 270.45 degrees Celsius. This is the baseline. This is the temperature of the universe itself. Think of the cosmos as a lukewarm oven that has been cooling for billions of years but hasn't quite turned off. Any object floating in deep space, far from any star, should eventually settle at this temperature. It cannot naturally get colder because the universe is constantly bombarding it with these microwave photons. The vacuum acts as a thermal bath, keeping everything at a minimum of 2.7 Kelvin. This was considered an unbreakable cosmic speed limit for cold. Nature simply does not have a refrigerator capable of going lower, or so we thought. In 1995, astronomers pointed the Swedish ESO sub-millimeter telescope toward a protoplanetary nebula 5,000 light-years away. They were observing a red giant star in its death throes, shedding its outer layers into the void. They expected to see gas cooling down to match the background of the universe. Instead, the data returned a number that shouldn't exist. The gas in this nebula, which we now call the Boomerang Nebula, was not 2.7 Kelvin. It wasn't in equilibrium with the cosmos. It was colder. The readings confirmed a temperature of 1 Kelvin. This is minus 272.915 degrees Celsius. This is just 1 degree above absolute zero. The Boomerang Nebula is significantly colder than the empty vacuum of space. It is colder than the radiation left over from the birth of the universe. It is a thermodynamic paradox. By all rights, the cosmic microwave background should be heating this gas up. The photons from the Big Bang should be warming it. Instead, the Boomerang Nebula is absorbing that heat, acting as a cosmic sinkhole, a frozen scar on the face of a microwave sky. It is the only known object in nature that has managed to dip below the temperature of the universe's background radiation, The discovery sent shockwaves through astrophysics because it implied that nature had found a way to cheat thermodynamic equilibrium. We have built machines on Earth that can reach lower temperatures, which we will discuss soon. But nature isn't supposed to have that kind of engineering. Nature tends toward balance. Heat flows from hot to cold until everything is equal. For a massive cloud of gas spanning light years to maintain a temperature of 1 Kelvin requires a mechanism of extreme violence and precision. Visually, the nebula reflects this ghostly nature. Through the Hubble Space Telescope, it appears as two asymmetrical lobes of gas, often described as a bow tie, reflecting the light of the dying star hidden deep within its dust. It looks serene, almost static. But this serenity is an illusion. We are witnessing a stellar catastrophe that has inadvertently created the most efficient cooling engine in the galaxy. The Boomerang Nebula proved that the floor of 2.7 Kelvin is not solid. It showed us that matter, under the most extreme conditions, can isolate itself from the energy of the Big Bang and descend into a realm of cold that was thought impossible for a natural object. But 1 Kelvin is still 1 degree of heat. It is still motion. To understand the true depths of cold, we have to go further. We have to look past the Boomerang Nebula and toward a limit that physics says we can never touch. A limit where motion stops, where time loses its meaning, and where reality itself freezes. The Boomerang Nebula brought us close, but the true monster we are chasing is absolute zero. And as we will find out, getting there is not just a matter of cooling things down. It is a battle against the fundamental laws of quantum mechanics. To understand the true nature of the Boomerang Nebula and why its existence is so baffling, we must first understand the destination it is trying to reach. We must look at the bottom of the thermometer. In our daily lives, cold is a sensation. It is the biting wind of winter or the ice in a glass. But to a physicist, cold does not exist. There is no such thing as cold energy or cold waves. There is only heat and the lack of it. Heat is simply the kinetic energy of atoms, the chaotic, jittering dance of particles bouncing off one another. The hotter the object, the faster the dance. The colder the object, the slower the rhythm. Therefore, logically, if you keep extracting heat, if you keep slowing the atoms down, eventually you should reach a point where the music stops completely, a state of total atomic paralysis. This theoretical endpoint is what we call absolute zero. 0 Kelvin. It is the holy grail of thermodynamics. It represents a state of perfect order and zero entropy, where the chaos of the universe is finally tamed into absolute stillness. But here is the problem. Absolute zero is a mirage. It is a destination that looks real on a graph, but in the physical universe, it is a forbidden zone. You can get tantalizingly close. You can get to within a billionth of a degree, but you can never, ever touch the zero mark. The laws of physics effectively conspire to prevent it. The first barrier is the third law of thermodynamics. This law dictates that as a system approaches absolute zero, the extraction of heat becomes exponentially more difficult. Imagine you are trying to walk to a wall, but the rules of the room say that each step you take can only cover half the remaining distance. You take a step and you are halfway there. You take another and you are 3/4 of the way there. You can take 1 billion steps and you will be microscopically close to the wall, but you will never actually touch it. This is the thermodynamic trap of cooling. To remove the final traces of heat from a system requires an infinite amount of work or an infinite number of steps. The universe demands a toll that cannot be paid, but the barrier goes deeper than just work and energy. It is woven into the quantum fabric of reality itself. Even if we had a magical machine that could suck every joule of thermal energy out of an atom, the atom would still refuse to stand still. This refusal is governed by the Heisenberg uncertainty principle. In the classical world, we are used to things having definite properties. A car is parked at a specific spot and has zero speed. But in the quantum world, particles do not behave like cars. They behave like probability clouds. The uncertainty principle states that you cannot know both the position and the momentum of a particle with perfect precision at the same time. The more precisely you pin down where a particle is, the less you know about where it is going or how fast it is moving. Now apply this to absolute zero. If an atom were to reach absolute zero, it would have zero thermal energy. It would stop moving completely. Its momentum would be exactly zero, and its position would be exactly fixed in space. We would know its position and its momentum with infinite precision. This violates the fundamental rule of quantum mechanics. Nature prohibits this level of certainty. So to protect the uncertainty principle, the atom retains a tiny, indestructible amount of residual motion. It jitters, it vibrates. This is called zero-point energy. It is the irreducible minimum energy that a quantum mechanical system must possess. Even in the deepest void, even if you could shield a box from the Big Bang and suck out all the heat, the atoms inside that box would still be humming with this quantum ghost energy. They are never truly at rest. The universe abhors stillness just as much as it abhors a vacuum. It forces matter to keep moving, to keep living, effectively making the true state of zero a physical impossibility. This redefines our understanding of what the Boomerang Nebula has achieved. When we say the nebula is at 1 Kelvin, we are not just saying it is very cold. We are saying that this cloud of gas has slowed down its atomic dance to a crawl, approaching the fundamental wall of reality where quantum mechanics begins to push back against classical physics. At 1 Kelvin, the thermal chaos is almost gone. The violent collisions of gas molecules that usually define a hot cloud have been pacified. So we have a paradox. On one hand, we have the cosmic microwave background heating everything to 2.7 Kelvin. On the other hand, we have the laws of thermodynamics making it exponentially harder to cool things down the lower you go. And yet, nature has spontaneously created a structure that defies the first and challenges the second. The Boomerang Nebula isn't just a cold spot. It is a natural engine that has overcome the baseline heat of the cosmos. To understand how this is possible, we have to stop thinking about cold as a static property and start thinking of it as a dynamic action. You don't get cold, you have to make cold. And to make cold in the vacuum of space, you need to perform a specific violent trick with geometry and speed. The Boomerang Nebula is doing exactly what our refrigerators do in our kitchens, but on a scale that dwarfs our solar system. It is expanding. And in physics, expansion is the ultimate thief of energy. The mechanism at play here is known as adiabatic expansion. It is a concept that sounds complex, but is actually something you experience every time you use a spray can. When you spray deodorant or compressed air, the can feels cold in your hand. Why? Because the gas inside was high pressure, and as it rushed out into the lower pressure of the room, it expanded. To expand, the gas molecules have to push against the outside world. They have to do work. And since energy cannot be created or destroyed, the energy to do that work has to come from somewhere. It comes from the internal heat of the gas itself. The gas pays for its expansion with its own heat, and as a result, its temperature plummets. The Boomerang Nebula is the ultimate cosmic spray can, but instead of a nozzle, it has a dying star, and instead of a room, it has the infinite void. The question is not just how it expands, but how it expands fast enough to outrun the heating power of the Big Bang's radiation. To find that answer, we must dive into the heart of the nebula itself, where a stellar tragedy is unfolding at speeds that boggle the mind. This is not a gentle cooling. This is a violent, high-velocity evacuation of heat that has somehow tricked the universe into allowing a temperature of 1 Kelvin to exist. We know the limit is impossible to reach. We know the universe tries to heat everything up. Now let's look at the machinery nature built to fight back. The Boomerang Nebula is not merely a static cloud floating in the void. It is a violent explosion frozen in time. To achieve a temperature of 1 Kelvin, colder than the empty vacuum, nature had to construct a machine of colossal proportions. The engine driving this phenomenon is hidden deep inside the cloud, obscured by a thick belt of dust so dense that visible light cannot penetrate it. For years, astronomers were puzzled by the sheer efficiency of the cooling. A standard dying star sheds its layers, yes, but usually at a leisurely cosmic pace, allowing the gas to remain relatively warm. The Boomerang Nebula, however, is shedding mass at a rate 100 times faster than a typical red giant. It is ejecting the equivalent of Neptune's mass every single year. This is not normal stellar evolution. This is a cataclysm. The leading theory suggests that the engine at the heart of the nebula is not one star, but two. A binary system. Imagine a massive red giant, bloated and dying, its outer atmosphere loosely held by gravity. Orbiting it is a smaller, denser companion star. As the red giant expands, it swallows the smaller star, or at the very least, interacts with it gravitationally in a common envelope phase. The smaller star acts as a cosmic blender, spiraling inward, churning the red giant's atmosphere and spinning it up to incredible speeds. This gravitational dance creates a centrifugal powerhouse, flinging the outer layers of the giant star outward with extreme ferocity. The result is a stellar wind that defies belief. In our own solar system, the solar wind streams off the sun relatively gently. In the Boomerang Nebula, the gas is being blasted out at speeds exceeding 164 kilometers per second. That is nearly 370,000 miles per hour. This is 10 times faster than the winds of a normal dying star, and it is this hypervelocity that holds the key to the temperature. Here is where the physics of the cosmic spray can becomes specific. The gas is ejected so fast that it outruns its own ability to exchange heat. In thermodynamics, this is called an adiabatic process. Adiabatic comes from the Greek for impassable. It means the process happens so quickly that no heat can enter or leave the system from the outside. The gas is essentially thermodynamically isolated. As this ultra-fast wind shoots out from the central star, it enters the emptiness of space and immediately finds itself unconfined. It expands rapidly, but expansion is not free. In the universe, there is a tax on everything. To expand, the gas molecules must physically push outward against their own internal pressure and the tenuous medium of space. This pushing requires energy. Since the gas is isolated by its speed, it cannot grab heat from the surrounding stars to pay this energy bill. It has no choice but to raid its own internal savings account. The savings of a gas cloud is its thermal energy, the vibration of its particles. So the gas converts its heat into the kinetic energy of expansion. It trades temperature for size. The mathematics of this trade are brutal. The gas starts at the surface of the star at thousands of degrees, but as it rushes outward and expands by a factor of tens of thousands, the temperature crashes. It plummets past the freezing point of water, past the liquefaction point of nitrogen, past the temperature of Pluto. It keeps dropping. Because the expansion is so rapid and so extreme, the gas overshoots the equilibrium point. It doesn't just cool to the background temperature of 2.7 Kelvin. The momentum of its expansion forces it to dump even more heat, driving it down to that impossible 1 Kelvin floor. The shape of the nebula acts as the nozzle for this engine. While it looks like a bow tie or a boomerang from our perspective, astronomers believe we are actually looking at a hollow hourglass shape from the side. The central belt of dust blocks the middle, and the gas shoots out the poles. This geometry channels the flow, focusing the expansion like a rocket nozzle, maximizing the cooling efficiency. It is a natural refrigerator the size of a solar system, powered by the gravitational death spiral of two stars. This is how nature beats the background heat of the Big Bang, brute force. It takes a star, rips it open, and flings its guts into the wicked at 500,000 kilometers per hour. It creates a pocket of cold so profound that it briefly defies the thermal logic of the universe. However, there is a catch. This state is temporary. The Boomerang Nebula is a transient phenomenon. Eventually, the expansion will slow. The gas will dissipate. The relentless bath of cosmic microwave background radiation will begin to win the battle, warming the gas back up to the universal standard of 2.7 Kelvin. The ghost will fade. Nature can only sustain this violation for a cosmic blink of an eye. Furthermore, 1 Kelvin is the limit of this method. Expanding gas has diminishing returns. You can only blow a bubble so fast before the physics of gas dynamics prevents you from getting any colder. Nature hits a wall at 1 Kelvin. It cannot reach the nanokelvin or picokelvin scales. It lacks the precision. Nature operates with explosions and gravity, blunt instruments that lack the finesse required to approach the quantum edge of absolute zero. To go colder, to truly freeze reality and see the quantum skeleton of the universe, we cannot rely on the chaotic death of stars. We need control. We need to stop atoms, not just spread them out. And to do that, human scientists had to invent something that sounds like a contradiction in terms. We had to figure out how to freeze matter using the hottest, purest source of energy we have. We had to learn how to cool things with lasers. This seems impossible. Lasers are pure energy. They cut steel. They burn retinas. They carry heat. How can you shine a beam of pure light onto an atom and make it freeze? The answer lies in a masterful manipulation of the Doppler effect and the momentum of light itself. We are about to leave the macro scale of nebulae and enter the micro scale of the quantum trap, where we will shatter nature's record by a factor of 1 billion. Nature uses violence to cool the universe. It rips stars apart and flings gas into the void to reach 1 Kelvin. But to go lower, to cross the barrier into the realm of the impossible, we had to abandon the brute force of astrophysics and embrace the delicate, paradoxical precision of quantum optics. We had to do something that sounds fundamentally wrong. We had to shine a light on the problem. In the 1970s and 80s, Physicists realized that to reach temperatures lower than the Boomerang Nebula, they couldn't just build a better freezer. They had to redefine the problem. Remember, temperature is motion. An atom at room temperature is a hysterical object. The air molecules breathing around you right now are zipping through space at roughly 500 meters per second, faster than a supersonic jet. To cool them down, you have to slow them down. You have to put the brakes on a particle moving at the speed of a bullet. The solution they found is one of the most elegant and counterintuitive masterpieces in the history of science: laser cooling. On the surface, this makes no sense. We associate lasers with heat. We use them to cut steel, burn retinas, and ignite fusion reactions. Shining a high-powered laser at a cloud of gas should cook it, not freeze it. But light has a secret property that becomes relevant at the atomic scale. Light carries momentum. Photons are massless, yes, but they still pack a punch. When a photon hits an atom and is absorbed, it transfers a tiny amount of kick to that atom, pushing it in the direction the light was traveling. Think of an atom as a bowling ball rolling down a lane. Think of a photon as a ping-pong ball. If you throw one ping-pong ball at a rolling bowling ball, nothing happens. The mass difference is too great. But if you fire 1 billion ping-pong balls per second, a relentless stream of impacts, you can actually slow that bowling ball down. This is the principle of laser cooling. We bombard atoms with a hail of photons to push against their motion. But there is a catch. If you just shine a laser beam at a gas cloud, you will hit atoms moving in all directions. You might slow down the ones coming toward you, but you will speed up the ones moving away from you. You would just add more chaos, which means more heat. You need a way to ensure that the laser only hits the atoms that are moving toward the light, creating a headwind that slows them down, while ignoring the atoms that are already stopped or moving the wrong way. The trick to solving this lies in the Doppler effect. We all know the Doppler effect from the sound of a passing ambulance. The siren is high-pitched as it comes toward you and low-pitched as it goes away. Light behaves the same way. If an atom is moving toward a laser beam, it sees the light wave as squashed or shifted toward the blue end of the spectrum, higher frequency. If it is moving away, it sees the light stretched or red shifted, lower frequency. Atoms are picky eaters. They will only absorb a photon if it is exactly the right color, the exact right frequency to bridge the gap between their electron energy levels. This is the key. Scientists tune their lasers to a frequency slightly below the frequency the atom actually wants. Here is the magic. If an atom is sitting still, the laser light is the wrong color, too red, too low frequency. So the photon passes right through like a ghost. The atom ignores it. But if the atom moves toward the laser, the Doppler effect shifts the light's frequency up just enough to make it the perfect color. Suddenly, the atom absorbs the photon. It takes the hit. The momentum of the photon kicks the atom in the opposite direction of its motion. The atom slows down. If the atom tries to move away, the light gets shifted even further into the red, the wrong direction, and the atom ignores it again. The laser acts as a selective trap. It only interacts with atoms that are misbehaving by trying to move toward it. Now, imagine setting up 6 of these lasers: top, bottom, left, right, front, back. No matter which direction the atom tries to fly, it runs into a laser beam that Doppler shifts into resonance and kicks it back to the center. It feels a viscosity, a drag force from the light itself. The atoms are swimming through a sea of photons, that feels like thick syrup. Physicists call this optical molasses. Inside this trap, the results are staggering. The chaotic jet speed motion of room temperature atoms is crushed. The atoms are slowed from hundreds of meters per second to a leisurely crawl of a few centimeters per second. The temperature plummets. We cross the 1 Kelvin line of the Boomerang Nebula without even blinking. We smash through the millikelvin barrier, 1,000th of a degree. We descend into the microkelvin range, millionths of a degree above absolute zero. At this scale, the Boomerang Nebula looks like a blast furnace. We have created a spot in the universe colder than anything nature can forge. In these laser traps, usually floating in the center of a vacuum chamber on Earth, we hold a small glowing ball of atoms, perhaps sodium or rubidium, suspended in the intersection of the beams. To the naked eye, it looks like a tiny glowing star, but it is a star of ice. We had achieved the impossible. We had used the purest form of heat, light, to create the purest form of cold. But science is never satisfied. As we peered into this optical molasses, we realized that microkelvins were not enough. There was still a limit. The lasers themselves were the problem. Remember the ping-pong ball analogy? Even though the laser cools the atoms, the individual impacts of the photons still cause a tiny amount of jitter. The atoms are being buffeted by the hail of light. This is called the recoil limit. The very cure was becoming the disease. The light that slowed the atoms down was also shaking them just enough to prevent them from reaching total stillness. We hit a wall at a few microkelvins. To break this wall and descend into the true abyss of the nanokelvin scale, billions of times colder than deep space, we had to turn the lasers off. We had to invent a way to cool matter in the dark. We needed a technique that didn't rely on hitting the atoms with anything at all. We needed to let the heat simply leave, like steam rising from a cup of morning coffee. Lasers brought us to the edge of the abyss, but they could not push us over. At the microkelvin scale, the very light that cooled the atoms became a source of heat. The pitter-patter of individual photons striking the atoms acted like a subtle drumbeat, keeping them vibrating, preventing them from settling into total stillness. To go deeper, to break the barrier of the recoil limit, we had to turn the lights out. We had to hold the atoms in the pitch black of a vacuum, without touching them, without hitting them with photons, and without letting them touch the walls of the container. How do you hold a cloud of gas in the center of a vacuum chamber without physical walls? You use the atom's own internal identity against them. Atoms are not just lifeless billiard balls. They are tiny magnets. They have a property called spin, which gives them a north and south pole. Under normal circumstances, these poles point in random directions. But if you apply a carefully shaped magnetic field, you can create a virtual bowl, a magnetic trap. In this trap, the magnetic field is weak in the center and strong at the edges. M's, with their magnetic poles aligned in a specific way, will feel a force pushing them toward the weak point, the center. They become trapped in an invisible cage made of pure magnetism. So scientists shut off the lasers. The optical molasses disappears. The room goes dark. The atoms are now caught in this silent magnetic bowl. They are hovering in the void, isolated from the universe. But they are still too hot. They are still vibrating with the residual energy left over from the laser cooling phase. To get them to the finish line, to the nanokelvin scale, physicists employ a technique that is surprisingly low-tech in concept, but high-tech in execution. They blow on the coffee. Think about how you cool a cup of hot coffee. You don't put ice in it, you wait. The hottest molecules in the liquid, the ones with the most energy, break the surface tension and escape as steam. When the most energetic molecules leave, they take their heat with them. The average energy of the remaining liquid drops. The coffee gets colder. This is evaporative cooling. It is the same reason you sweat to cool down. In the magnetic trap, physicists perform a controlled version of this. They treat the magnetic field like the walls of a cup. By tuning the magnetic field, often using radio waves to flip the spin of the atoms, they can effectively lower the height of the walls. They lower the lip of the magnetic bowl just enough so that the most energetic, hottest atoms can jump over the edge and escape into the vacuum. These hot atoms are sacrificed. They are ejected from the trap forever. What remains in the trap are the slower, colder atoms. These atoms collide with each other, redistributing their energy and settling into a new, lower average temperature. Then, the scientists lower the walls again. They cut deeper. The next batch of fastest atoms escapes. The remaining cloud gets colder and denser. They repeat this process, shaving away the hottest layers of the gas over and over again. It is a thermodynamic culling. We are distilling the cloud, throwing away the chaos and keeping only the calm. As the evaporation continues, the temperature freefalls. We leave the micro-Kelvin scale behind. We enter the nano-Kelvin zone, billionths of a degree above absolute zero. At this stage, the atoms are moving so slowly that if you could see them, they would appear to be barely drifting. They are colder than the depths of space by a factor of millions. The density of the cloud increases as the atoms huddle together in the bottom of the magnetic bowl. We are now traversing a desert of physics where no natural object has ever set foot. The Boomerang Nebula is a blast furnace compared to this. We are so close to the fundamental limit of existence that the classical laws of physics, the rules that govern bouncing balls and orbiting planets, begin to tremble and fail. But this isn't just about making things cold for the sake of setting a record. We are cooling them because we are hunting for a monster. Decades ago, Albert Einstein and Satyendra Nath Bose predicted that if you could get atoms cold enough, if you could pack them together in this frozen density, something impossible would happen. They predicted that the atoms would undergo an identity crisis. They claimed that at a critical threshold of cold, the atoms would stop behaving as individuals and merge into a single, giant, coherent entity, a new state of matter that is neither solid, liquid, gas, nor plasma. For 70 years, this was just a mathematical ghost story, a piece of paper with an equation that seemed too strange to be real. But as the temperature in these magnetic traps dropped lower and lower, slicing through the nano-Kelvin range, the data on the monitors began to change. The atoms were getting closer. The phase transition was approaching. The scientists were no longer just cooling gas. They were forcing reality to crash. And then, in 1995, in a laboratory in Colorado, the last barrier broke. The temperature hit a critical low, 170 nano-Kelvins, and the universe did something it had not done since the Big Bang. For 70 years, the Bose-Einstein condensate was a ghost story. It was a mathematical prediction that sat on the dusty shelves of theoretical physics, widely accepted as true, but believed to be impossible to actually create. In the 1920s, Indian physicist Satyendra Nath Bose sent a letter to Albert Einstein containing a new statistical method for counting photons. Einstein, recognizing the brilliance of the work, translated it and extended the logic to matter itself. The math whispered a strange secret. If you could get a specific type of atom, known as a boson, cold enough, the rules of individuality would vanish. To understand why this happens, you have to accept a fundamental truth of quantum mechanics that our brains struggle to visualize. Matter is not solid. An atom is a particle, yes, but it is also a wave. It has a wavelength. At room temperature, or even in the burning heart of a star, an atom's momentum is high, which means its wavelength is tiny, infinitely smaller than the distance between atoms. In this state, atoms act like billiard balls. They bounce off each other. They are distinct. They are individuals. But as you cool an atom, you steal its momentum. And according to the equations of quantum mechanics, as momentum drops, wavelength grows. The fuzziness of the atom expands. Einstein predicted that if you cooled a gas to within a hair's breadth of absolute zero, the atoms would become so sluggish and their wavelengths so long that they would begin to overlap. And then, a catastrophe of identity would occur. The waves would not just mix, they would merge. The atoms would undergo a phase transition unlike anything in classical physics. They would collapse into the exact same low-energy quantum state. They would lose their individual boundaries. They would stop being atoms in the plural sense and become a single, coherent entity. For decades, this was just an equation on paper. But on June 5th, 1995, inside a lab at the University of Colorado Boulder, physicists Eric Cornell and Carl Wyman finally pushed the button that broke reality. Using the laser cooling and magnetic evaporation techniques we just explored, they drove a cloud of 2,000 rubidium atoms down to 170 nanokelvins. Suddenly, the data on their monitors transformed. They were looking at a velocity distribution graph, a map of how fast the atoms were moving. For a normal gas, this looks like a gentle round hill, but as the temperature hit the critical threshold, a sharp, dense spike erupted from the center of the graph. It rose like a needle out of the flat plains of thermal noise. This spike was the smoking gun. It was the visual proof that thousands of individual atoms had suddenly snapped into synchronization. They had locked together. They were no longer a collection of particles buzzing around in a trap. They were a single superatom. They had formed a Bose-Einstein condensate, BEC. This was the discovery of the fifth state of matter. We are taught in school that there are three states: solid, liquid, and gas. Science later added plasma. But the BC is stranger than all of them combined. In a solid, atoms are fixed in place, but they still vibrate individually. They have their own addresses. In a BC, the atoms are not just fixed, they are the same. Think of a crowd of people walking through a city square. That is a gas, disordered individual energy. Now, imagine that every single person in that crowd suddenly stops, loses their unique features, their height, their face, their name, and transforms into the exact same hologram. They begin to move in perfect unison, stepping with the same foot at the exact same time. They become a single blurry wave of humanity. That is a Bose-Einstein condensate. The creation of the Beck was not just a record-breaking temperature reading. It was a philosophical earthquake. It broke the wall between the microscopic and the macroscopic. Usually, quantum mechanics, the weird behavior of waves and probability, is hidden deep inside the atom. It is invisible to us. But a Beck is a quantum object amplified to the size of a grain of sand. It is a quantum wave you can almost poke with a stick. For the first time in history, We weren't just inferring quantum mechanics from math. We were looking at it. The scientists had forced matter to obey a single will. They had frozen the chaos of the universe into a state of perfect order. But as they looked closer at this blob of super-cold rubidium, they realized that frozen was the wrong word. The superatom wasn't dead. It was behaving in ways that defied common sense. When you create a state of matter that shouldn't exist, you start seeing properties that shouldn't exist. We had opened the door to the quantum realm and invited it into our world. And the first thing we noticed was that this new form of matter didn't just look different. It acted like it was haunting the laboratory. The duality of particle and wave was no longer a theory. It was now a visible, tangible monster. To look upon a Bose-Einstein condensate is to look at a glitch in the matrix. It is one of the few times in human history where we can point to a spot in space and say, there is no variety there. There is only one thing. When you cool atoms to this extreme, you are effectively erasing the information that makes them distinct. You are smoothing out the roughness of reality. In a normal gas, even a very cold one, the atoms are like dust motes floating in a sunbeam. They are distinct specks. If you took a picture, you would see a scattershot of points. But in a BC, that picture changes. The atoms blur. They don't just slow down. They spread out. Their physical boundaries dissolve. They become a single, hazy blob of quantum potential. This is the superatom. It is a concept that is difficult to wrap your head around because our brains are wired for a classical world. We are used to things being in one place at one time. A chair is here, a table is there, but inside the magnetic trap, the Beck is everywhere at once within its confinement. It is a giant probability wave. If you were to ask, where is atom number 45? The answer would be, it is everywhere. Every atom occupies the entire volume of the condensate simultaneously. The most striking proof of this comes when you try to smash two of these things together. If you take two clouds of normal gas and throw them at each other, they crash. The atoms bounce like marbles. They scatter. It is a messy collision of particles. But if you take two Bose-Einstein condensates and let them overlap, they don't crash. They pass through each other like ghosts, but they leave a mark. As the two waves of matter overlap, they create an interference pattern. It looks exactly like the ripples formed when you throw two stones into a calm pond. You see alternating bands of light and dark, stripes of matter and empty space. This is the smoking gun of the quantum world. These stripes are regions where the waves of the atoms either amplify each other or cancel each other out. Where they cancel out, there are no atoms. The matter simply vanishes from that spot because the wave said zero. This is the visual confirmation that matter, at its heart, is not made of solid little balls. It is made of waves. And at nanokelvin temperatures, those waves become large enough for us to take pictures of them. We are seeing the machinery of the universe exposed. We are looking at the code behind the screen. This state of matter allows us to do things that sound like magic. Because the atoms are locked in phase, marching in perfect lockstep like a regiment of soldiers, we can manipulate them with incredible precision. Scientists have used Becks to slow light down, not just a little bit. In a vacuum, light travels at 300,000 kilometers per second. By shooting a laser through a Bose-Einstein condensate, physicists have managed to slow a pulse of light down to the speed of a bicycle. They have even brought light to a complete stop, trapped it inside the cold cloud, and then released it later. The BEC acts as a cage for light itself, using the extreme density and quantum properties of the atoms to drag on the photons like they are moving through molasses. This leads us to a profound realization. The temperature of a Beck is not just a number on a thermometer. It is a threshold where the rules of the game change. The fuzziness of quantum mechanics is usually confined to the subatomic world because thermal noise, heat, scrambles it. Heat hides the quantum nature of reality. It shakes things up so much that the waves get messy and look like particles. By cooling matter to within a whisper of absolute zero, we are quieting the noise. We are silencing the static so we can hear the clear, pure note of the universe. But the visual spectacle of the superatom is only the beginning. When matter loses its individuality, it also loses its ability to interact with the world in normal ways. It stops playing by the rules of friction. If you thought a gas that behaves like a wave was strange, wait until you see a liquid that refuses to stop moving. Wait until you see a fluid that can flow upward against gravity and spin forever without losing energy. We have frozen the atoms into a single wave. Now, let's watch what happens when that wave decides to flow. When we freeze matter into a quantum state, we don't just get strange statues made of waves. We get motion that defies the laws of mechanics. If the Bose-Einstein condensate is the ghost in the machine, then superfluidity is the machine running without an engine. It is the death of friction. To understand why this matters, look at the world around you. Everything that moves eventually stops. If you slide a puck across ice, it slows down. If you stir a cup of coffee and walk away, the swirling stops. This is the tyranny of friction and viscosity. In our universe, motion costs energy. Atoms rub against each other, turning kinetic energy into heat, dissipating the order of motion into the chaos of thermal vibration. It is an inescapable tax we pay for existing in a physical reality. But at temperatures approaching absolute zero, specifically in isotopes like helium-4, when cooled below 2.117 Kelvin, a threshold known as the lambda point, that tax is repealed. The liquid transforms into a superfluid, and suddenly the rules of viscosity vanish. If you were to stir a cup of superfluid helium, it wouldn't just swirl for a few minutes. It would swirl for an hour, a year, a century. In fact, if you could keep the temperature low enough and the container sealed, it would rotate forever. It would continue to flow until the end of time, or until the heat death of the universe interferes. It creates a perpetual motion of currents that requires no energy input to sustain. The fluid slips past the walls of the container and past its own atoms with zero resistance. It has achieved perfect, frictionless flow. But the lack of friction leads to behavior that looks less like physics and more like a horror movie. If you place superfluid helium in an open beaker, it will not stay there. It will seemingly become alive. Because there is no friction to hold it back, the forces of attraction between the helium and the container wall dominate. The fluid forms a film, a layer just one atom thick that creeps up the side of the glass. It defies gravity. It climbs up the walls, flows over the rim, and drips down the outside of the beaker until the container is empty. It is a liquid that actively escapes its prison, flowing uphill to find a lower potential energy state outside. This is the Rollin film, named after physicist Bernard Rollin. It is a macroscopic demonstration of quantum mechanics. The atoms are trying to spread themselves out as much as possible, and without friction to stop them, they simply walk out of the cup. Even stranger is what happens if you try to spin the container. In a normal liquid, if you rotate the bucket, the fluid eventually rotates with it. In a superfluid, If you rotate the bucket slowly, the fluid stays perfectly still. It ignores the walls. Because there is no friction, the walls cannot grab the liquid to pull it along. The bucket spins, but the helium inside remains stationary, floating in perfect detachment from its container. If you spin the bucket faster, the fluid doesn't just start to turn chaotically. It breaks into quantized vortices. Tiny, discrete tornadoes form inside the liquid. These aren't random swirls. They are precise mathematical structures. The fluid can only rotate at specific speeds allowed by quantum mechanics. It's as if the liquid has gears. It is nature showing us that even the flow of water, something we think of as smooth and continuous, is actually made of jagged digital steps when you look close enough. Superfluidity proves that the impossible lack of resistance is real. It is a glimpse into a world where energy is not lost, where motion is eternal, and where matter flows through the tiniest cracks, even through ceramic pores so small that air molecules cannot pass through them. A superfluid will leak through a container that is watertight and airtight because it slips through the molecular gaps of the material itself. We have mastered these fluids on Earth. We use them to cool the magnets in the Large Hadron Collider and in MRI machines. But doing this on Earth is hard. Gravity is a bully. It crushes the delicate quantum states. It pulls the atoms down, smashing them against the bottom of the trap, forcing us to use immense amounts of energy just to hold them in place. Gravity limits how cold we can get and how long we can observe these fragile quantum dances. To go further, to see the true face of the cold, we had to leave the planet. We had to take the most sensitive freezer ever built and launch it into orbit, where gravity could no longer interfere. We had to build a laboratory in the vacuum of space. Gravity is the enemy of the cold. On Earth, every time we try to cool atoms down to the quantum limit, we are fighting a losing battle against the planet beneath our feet. Gravity is relentless. It pulls on the atoms in the magnetic trap. To stop them from falling to the bottom of the vacuum chamber and hitting the floor, which would instantly heat them up and destroy the condensate, we have to make the magnetic trap strong. We have to tighten the invisible walls to hold the atoms up against the pull of the Earth. But tightening the trap comes with a cost. A tight trap compresses the gas. Compression creates density, and density creates collisions. Collisions create heat. It is a vicious cycle. We want the atoms to expand and cool, but if we let them expand too much, gravity pulls them out of the observation zone. On Earth, when we turn off the trap to let the atoms expand and cool further, they fall. We only have a few milliseconds to take a picture before they drop out of the frame of our cameras. We are trying to study the most delicate state of matter in the universe while it is literally falling off a cliff. To break this stalemate, we had to remove the planet from the equation. We had to build a refrigerator and shoot it into the sky. In May 2018, a Cygnus cargo spacecraft launched from Wallops Island, Virginia, carrying a payload that would rewrite the record books. It was the Cold Atom Laboratory, or CAL. Its destination was the International Space Station. The CAL is a physics laboratory the size of an ice chest. It was installed by astronauts, but is operated by remote control from the Jet Propulsion Laboratory in California. And inside this box, orbiting 400 kilometers above our heads, scientists have created the true coldest place in the known universe. The advantage of the ISS is not that it is far from the sun. It isn't. It's that it is in a state of perpetual freefall. It is in microgravity. Inside the CAL, the atoms don't fall down because the entire room is falling with them. This changes the game of thermodynamics completely. Because gravity is no longer pulling the atoms down, the scientists don't need a strong magnetic trap to hold them up. They can make the trap incredibly weak. They can barely hold the atoms at all. And when they turn the trap off to let the atoms undergo adiabatic expansion, the cloud doesn't drop, it floats. It hovers in the center of the vacuum chamber. On Earth, we have milliseconds to watch the expansion before gravity ruins the experiment. In the cold atom lab, the atoms can float and expand for 5, 10, even 20 seconds. In the world of quantum mechanics, this is an eternity. It allows the expansion to continue long past the point where it would have stopped on Earth. The gas can get fluffier, larger, and infinitely colder. With this freedom, the cold atom lab has smashed the barriers set by terrestrial labs. While the best labs on Earth struggle to get below the nanokelvin range, billionths of a degree, the CAL has pushed into the picokelvin range. A picokelvin is 1/trillionth of a degree Kelvin. It is a number so small it borders on the meaningless. To put it in perspective, a picokelvin is to a degree what a single footstep is to the distance between Earth and Saturn. In this box on the ISS, atoms are moving so slowly that it would take them lifetime to cross the width of a human hair. At these temperatures, the wave nature of the atoms becomes the dominant reality. The matter waves grow to be macroscopic. We can see quantum interference patterns with unprecedented clarity because the sample isn't crashing into the floor. It is suspended in a pristine, gravity-free void. This confirms a staggering fact. The coldest place we know of is not the dark side of the moon. It isn't the Boomerang Nebula in deep space. It isn't even in a university basement. It is currently flying over your head at 17,500 miles per hour. We have taken the crown from nature. We have built a bubble of cold so extreme that it makes the vacuum of space look like a roaring fire. The Cold Atom Lab has allowed us to verify that the laws of physics hold true even at the bleeding edge of existence. But it also hinted at something else. As we mastered the control of these quantum states, playing with magnetic fields to freeze atoms into submission, we stumbled upon a quirk in the math. A loophole in thermodynamics that suggests the scale doesn't just go down to zero. We have spent this entire journey trying to get to the bottom of the thermometer. We assumed 0 Kelvin was the floor. We assumed you cannot go lower than 0. But in the twisted logic of quantum mechanics, 0 might not be the end. Under very specific, highly unstable conditions, it is possible to trick nature into creating a temperature that is technically negative. But be warned, negative temperature does not mean colder than absolute 0. It means something far more volatile. It means we are about to break the definition of heat itself. We have spent this journey descending a mountain. We started at the scorching heat of stars, passed through the temperate zone of Earth, crossed the freezing void of deep space, and drilled down through the microkelvins and picokelvins, finally arriving at the base of the cliff, absolute 0. We view 0 as the ground, the end of the line, a wall where the math stops. But what if I told you that the temperature scale is not a straight line? What if it is a circle? And what if, by manipulating the laws of entropy, we can step off the edge of absolute 0 and not fall into nothingness, but reappear on the other side? This brings us to the most mind-bending concept in thermodynamics: negative absolute temperature. To understand this, we have to delete the definition of temperature you learned in school. You were likely taught that temperature is simply the average speed of atoms. Fast atoms are hot, slow atoms are cold, stopped atoms are 0, By that logic, you can't have negative speed, so you can't have negative temperature. But to a physicist, temperature is defined differently. It is defined by entropy, the measure of disorder. Specifically, temperature is a measure of how much the disorder of a system increases when you add energy to it. Under normal conditions, in everything from a cup of tea to a star, most atoms prefer to be in a low energy state, chilling at the bottom, while only a few have enough energy to bounce around at high levels. This is the natural order. If you add energy, you push more atoms up into the high energy states, increasing the chaos. Disorder goes up. Positive change equals positive temperature. This is the Boltzmann distribution. It is the rule that governs the universe. But in the quantum traps we have discussed, we can cheat. Using lasers and magnetic fields, scientists can manipulate atoms into a state known as population inversion. Imagine a valley full of balls. Naturally, they all roll to the bottom. That is 0 Kelvin. Now imagine we instantly flip the landscape. Suddenly, all the balls are balanced precariously on top of a sharp peak. They are all in the highest possible energy state simultaneously, with none at the bottom. In this precarious, unnatural state, the rules of entropy reverse. If you were to add more energy to this system, you wouldn't increase disorder, you would actually decrease it because the atoms are already maxed out. The math of thermodynamics looks at this situation, where adding energy reduces entropy and spits out a result that seems like a glitch. The temperature is negative. But here is the twist that melts the brain. Negative 0 is not colder than absolute 0. It is not super frozen. In terms of heat flow, a system with negative absolute temperature is hotter than any positive temperature in existence. It sounds insane, but follow the logic of heat flow. Heat always flows from the object that wants to lose energy to the object that wants to gain it. A negative temperature system is a system bursting with energy, with every atom piled at the maximum limit, desperate to collapse back down to the bottom. It wants to give away energy more than a supernova does. If you were to touch an object at -1 Kelvin to an object at +1 billion Kelvin, heat would flow from the negative object to the positive one. Therefore, on the true cosmic scale of thermodynamics, negative absolute temperature sits above positive infinity. The scale wraps around. You start at +0 Kelvin, go up through room temperature, past the sun, past infinite heat, and then you cross over into negative infinity, and come down through negative temperatures, back toward -0 Kelvin. We have actually created these states in the lab. In 2013, physicists at the Ludwig Maximilian University in Munich used potassium atoms to achieve a negative absolute temperature. For a brief, fleeting moment, they held a gas that was technically hotter than the Big Bang, yet stable in a vacuum trap. This discovery shattered the linear view of the universe. It proved that cold and hot are relative concepts tied to the statistical arrangement of atoms, not just their speed. It showed us that we can trick the laws of nature into running backward. However, these states are unstable. They are fleeting islands of impossibility that collapse the moment they interact with the outside world. They are not the fate of the universe. The fate of the universe, the real, inevitable destiny of the cosmos, is something much simpler and much more terrifying. While we play with negative temperatures in our labs, the universe itself is sliding relentlessly in the other direction. We are returning to the concept of the Big Freeze. We have looked at the coldest places we can find or make now. But what about the coldest place that will ever exist? To see the ultimate cold, we have to fast forward the clock. We have to look past the death of the sun, past the death of the galaxies, and peer into the deep time of the future. We are heading toward a state where the Boomerang Nebula will look like a bonfire, and where the concept of temperature itself may cease to have meaning. We are heading toward the heat death. The labs on Earth and the stations in space are merely pockets of resistance. We build our magnetic traps and laser lattices to create islands of cold, fighting against a universe that is still, for the most part, warm and alive. We are surrounded by burning stars, colliding galaxies, and the microwave hum of creation. But this warmth is temporary. We are living in a brief golden afternoon in the lifespan of the cosmos. The sun will set, and when it does, the universe itself will become the ultimate refrigerator. The destiny of the universe is defined by the second law of thermodynamics. It states that entropy, disorder, always increases. Energy spreads out. It flows from concentrated sources like stars to empty spaces. It seeks equilibrium. Right now, the universe is rich in contrast. We have hot stars and cold vacuums. This difference drives everything: life, weather, machines, time. But eventually, the differences will smooth out. The fuel will run out. We are heading toward the era of the Big Freeze. As the universe continues to expand, driven by dark energy, the distance between galaxy clusters will grow so vast that light can no longer bridge the gap. The cosmic microwave background, that 2.7 Kelvin bath we discussed at the start, will be stretched thinner and thinner. In a few billion years, it will drop to 1 Kelvin, then to 0.1 Kelvin. It will fade into radio waves, then into wavelengths longer than the universe itself is wide. The oven of the Big Bang will finally turn off. In about 100 trillion years, the last star will be born. When it burns out, the age of starlight will end. The universe will go dark. The only sources of heat remaining will be the cooling corpses of white dwarfs and neutron stars, fading slowly into black dwarfs. These too will eventually reach the temperature of the void. But there will be one last holdout against the cold: the black holes. For eons, these gravitational monsters will dominate the dark cosmos. And here lies a final, beautiful irony of physics. According to Stephen Hawking, black holes are not perfectly black. They emit a faint trickle of particles known as Hawking radiation. They have a temperature, but the math is inverted. The more massive a black hole is, the colder it is. A supermassive black hole, like the one at the center of our galaxy, has a temperature so low it is almost impossible to write down. It sits at roughly 10 to the power of negative 14 Kelvin. That is a decimal point followed by 13 zeros and a 1. It is a quadrillionth of a degree above absolute zero. It is far colder than the Boomerang Nebula, colder than our best labs, colder than anything we can imagine. In this deep future, these behemoths will be the coldest objects in existence, absorbing the last stray photons of the dying universe. But even they are not immortal. As they emit radiation, they lose mass. As they lose mass, they get hotter, though still freezing by human standards, and radiate faster. Over timescales that defy comprehension, years numbered with a 1 followed by 100 zeros, the black holes will evaporate. They will shrink, glow, and finally vanish in a flash of gamma rays. When the last black hole evaporates, the heat death is complete. The universe will consist of a thin soup of photons and subatomic particles, separated by light years of nothingness. The expansion of space will have stretched these particles so far apart that they will never interact again. The temperature will approach absolute zero asymptotically. It will be 0.000, repeating forever, never quite touching the mathematical bottom, but for all practical purposes, dead. There will be no more heat flow, no more energy transfer, no more time, because time requires change, and nothing will ever change again. This is the cold in its most terrifying form. It is not just the absence of heat, it is the absence of future. The silence will be total. The Boomerang Nebula, the cold atom lab, the lasers, the magnetic traps, they were all just fleeting sparks trying to understand the dark before the lights went out forever. This realization transforms our understanding of the cold. We often fear the cold as a force of death, but in our current era, the cold we create in labs is a tool of discovery. It is vibrant, it is active, it reveals the quantum heartbeat of reality. But the cosmic cold, the big freeze, is the true end. It is the canvas upon which the story of the universe is painted, and eventually, the canvas will be all that is left. So why does this matter? Why spend billions of dollars and the brightest minds of our generation to race toward absolute zero now, if the universe is going to take us there anyway? Why build these machines to freeze atoms when the ultimate freeze is inevitable? The answer lies not in the destination, but in what we found in the mirror. We explore the cold, not to prepare for the end, but to understand the beauty of the present. Our journey began with a paradox, a dying star in the Centaurus constellation that managed to become colder than the empty space around it. The Boomerang Nebula showed us that nature has engines of immense power, capable of carving out pockets of isolation in a hot universe. But our journey didn't stop there. We realized that to see the true face of reality, we had to go where nature could not. We had to build our own engines. We learned to use light to freeze matter. We learned to trap atoms in magnetic bowls and shave away their energy until they sat still. And when we did, we were rewarded with a vision of the impossible. We saw atoms lose their identity and merge into a single quantum wave. We saw fluids flow without friction, defying gravity and time. We saw the fundamental jitter of the universe exposed, no longer hidden by the chaos of heat. This is the great lesson of the cold. Heat is noise. Heat is confusion. It scrambles the signal. It makes atoms bounce and collide, masking their true nature. By stripping away the heat, by forcing the universe down to the picokelvin scale, we silence the noise. And in that silence, we heard the quantum music that plays underneath everything. We discovered that the solid reality we think we live in is actually made of ghostly waves and probabilities, and that the rules of the everyday world are just a special case of a much stranger, deeper truth. There is a profound irony in our quest for absolute zero. We are creatures of heat. Our biology relies on chemical reactions that require warmth. Our civilization is built on fire, steam, and combustion. We are the children of stars. And yet, we are obsessed with the cold. We spend lifetimes and fortunes trying to reach a place where life cannot exist, where motion stops, and where time freezes. Why? Because we are the part of the universe that wants to know itself. The heat death is inevitable. The big freeze is coming. In the grand calculus of the cosmos, the era of stars and life is just a brief spark in an eternal night. But that spark matters. The fact that we are here right now, in this warm, vibrant window of time, with the intelligence to build machines that can freeze atoms and the imagination to predict the end of time, is a miracle of probability. We have looked into the abyss of the cold, and instead of finding nothing, we found the keys to the universe. We found the fifth state of matter. We found the connection between thermodynamics and information. We found that even in the deepest void, reality is rich, complex, and waiting to be understood. The universe may one day freeze into eternal silence, but until that day comes, we will continue to light our lasers, build our traps, and push the boundaries of the impossible. We will continue to chase the zero, not because we fear the dark, but because it is only in the dark that we can truly see the light. The coldest place in the universe is not a dead nebula, and it is not a laboratory on a space station. The coldest place is the future that awaits us all. But the journey to understand it, that is the warmest, most human thing we can do.